All right, hello everybody. I'll just wait for a few more minutes as people are trickling in. Welcome to the Superbio and Google Health webinar about CXR Foundation. Super happy that you're here. We're gonna get started in a few minutes. Hi, Andrew.
Hey, how's it going? Can you hear me?
Yes, we can hear
Awesome.
you well. Will Rory be joining?
He will. I don't know where he is now, but he should be here soon. I can ping him.
Okay, sounds good. Sounds good. I'll just wait another minute and I'll kick things off.
It looks like Rory is here, I think, actually.
Oh, okay.
Apologies.
Hello.
Zoom is not my usual VC software.
Not a problem. Not a problem. Well, thanks for everyone joining in. Thank you, Rory, and thank you, Andrew. Welcome to Superbio Google Health's CXR Foundation webinar. Today we have two esteemed guests from Google Health, Google Research, Rory Pilgrim and Andrew Sellergren. Before I pass it down to them to talk about their very cool work, I just wanted to introduce Superbio very briefly for those who are looking to also here to learn a bit more about what we do. We'll just be very briefly. So we are Superbio. Let me share my screen. Do let me know if you can't see my screen. We're Superbio. We are here to democratize AI for biotechnology. Essentially, Superbio is a low-code AI platform and marketplace for biomedical AI. What we're looking to do, we're looking to bring tools, research enabling tools from research to impact. On one side, we have developers like major research organizations, universities, academic medical centers, tech companies. Some examples are Stanford, Google Health, Johnson & Labs, MSK. These are organizations, just as an example, no official affiliation. On the other hand, we have users such as health systems, biopharma companies such as Cleveland Clinic, Harvard, and AbbVie, right? So Superbio platform and company sits right in the middle. What we do is we crowdsource AI-based tools, machine learning models from open source developers and commercial developers, and then we place them in an optimized user interface and cloud in a collaborative workspace, and then we provide these tools to users that I have outlined in the previous slide, right? Health system, biopharma companies, and research organizations. And whatever we receive, new revenue, we actually give it back to the community of researchers, right? If you're an open source developer, you get credits and rewards and revenue share from our platform, as well as visibility in community alongside the best AI researchers in the world who are working on life sciences problem. And if you're a commercial dev, then you can basically generate an entire new additional revenue stream and then access a global market through the Superbio platform, right? This platform is already out. We have over 600 research enabling tools, few of them which are CXR Foundation and and apps that we have derived from CXR Foundation as Superbio. With the platform, you can run inference, retraining, fine-tuning through no-code applications or APIs, and access the community models, as well as hosting your own models. And you can collaborate with your team on board as a team to share models and results with your team. And as part of our our giving back to the community, we run these webinars pretty frequently. Last month we had one with Hantin Quiz, a PhD student, the lead author of XGPT single cell GPT model. Today we're joined by Rory Pilgrim and Andrew Sellergren, Google Research, Google Health researchers, and we also run a blog called Superbio Scientist Spotlight, where we interview and publish those interviews with prominent researchers who have contributed or who are looking to contribute to the life sciences field through AI or other impactful technologies. So without further ado, Rory and Andrew, thank you so much for joining. I'll pass it to you to talk more about CXR Foundation, its origin stories, and everything about it.
Thanks so much. Let me just get some slides up here. I'll just give you a bit of background before we go into some of these demos about what CXR Foundation is and why we think it's a really exciting tool for people to be able to use. So myself and Andrew are part of Google Research Health AI. So we think about how do we
Rory, I think your microphone got cut off because I don't think we can hear you.
Is that better there?
Yep, can hear you.
Sorry, Zoom is not my friend. As I was saying, we think it's really important that we can help other people build applications within medical imaging so they can improve their workflow within radiology, within dermatology, within pathology. Obviously, today we're talking about radiology. And we think about chest x-rays as a starting off point. Chest x-ray is a dominant modality for medical imaging. So many chest x-rays, billions are generated every year. And we think that when it comes to people actually understanding how to derive more value from this medical imaging, AI serves a big role there. But unfortunately, for a lot of people in clinical fields, it's really hard to get started with this. You need to sort of know about machine learning. You need to have a lot of data, and that can be really challenging. So we wanted to build CXR Foundation as a tool to help people get started with less data, setup, and compute. So we put this paper out there. You can see Andrew, first author on the paper, and he's here today. So please encourage people to ask questions of Andrew. But this is our transfer learning for chest radiography, where we're trying to help people build applications with what we call an embeddings model without less data, so they can actually focus on the tasks that they really care about. So the way this works is that we train an embeddings model on millions of x-rays that we have at Google Research, and we sort of create this baseline model that understands the chest x-ray modality. And from there, we make that available for people so they can build on top of that using their own data that's task-specific. But the upshot of that is that task-specific data can be much, much smaller in volume than traditionally you would need in machine learning. So you can see some plots here from our paper where we showed that with as little as 64 images, 8 squared, you can get really good performance. And obviously, it does go up with a little bit more data, but you need much, much less data than you would traditionally need for machine learning tasks, where you need things like millions of images, tens of thousands of images. And what's really exciting for us is that this actually generalizes across lots of different tasks within chest x-rays. So whether it be sort of standard diagnostic tasks, complicated things like tuberculosis and COVID, we find that the CXR Foundation tool can be really helpful for people who want to develop on top of it. And just to give you a sense for what this actually means, an embedding is a multi-dimensional vector that we output from the model and serve to you and provide to you that you can then train a linear probe or some other machine learning model to interpret that vector and get some sort of insight. And why it's really powerful is when you look at the embeddings from sort of general image tasks, you can see they're not very organized in the chest x-ray space. So what this is trying to represent here is a 2D representation of the embeddings. So it's a simplification. And we've got images here plotted on this 2x2 chart, and you can see we have labels in red for airspace opacity positive and blue for airspace opacity negative. And for the general network embeddings, they're not really clustered in any way that makes sense. You can't really look at those and actually derive a pattern or try and easily learn some sort of clustering that would help you actually distinguish between the positive and negative. And that's not true, of course, when we use the CXR network embeddings. When we do that, you can see that the red and blue are very well distinguished. So we're able to actually look at these separately, and you can actually train a model that's able to draw that boundary and actually get a really good performance in terms of differentiate that just out of the box, because you've got that pattern emerging naturally because of the CXR pre-training we've done. Just pause there. Andrew, anything you want to add on the embeddings there? Andrew is the technical guy, so I'll let him add more about how the embeddings work.
No, it's a great explanation. I'll just add that another way of thinking about the embeddings is as compression. So, just similar to how you might compress a video before you send it. If you take this chest X-ray, which might be 2,000 or 3,000 by 3,000 pixels, so several million pieces of information, and then what you send actually, or what results from the network is only a few thousand numbers. So there's a big amount of compression there. Rory, are you?
Rory, can you hear us? You cannot hear us. Right.
I just fixed my audio. Sorry, like I said,
no problem.
Zoom is not. Andrew, anything? I didn't hear anything you said. So
okay, yeah, I went ahead and added my bit about embeddings as information compression. So so you're good to go. Yeah.
Awesome. So in terms of what we can do with these embeddings, we've seen sort of over 150 customers sign up and actually use this tool. Some of them use it in Superbio, and we've seen a variety of different applications within the chest X-ray space. So some of these are operational. So these are things like non-diagnostic classifications that help workflows happen more efficiently. So whether that be checking image quality, looking at laterality, understanding what kind of study is actually in the packs. That's something that people are interested in doing. We also have screening applications where we're trying to do more with radiologists to make their time more efficient by pre-identifying cases that need urgent review, or potentially look at things that are normal that don't actually need as much review at all. And then, of course, some people are building applications in specific diagnostics, whether these be things like cardiomegaly, consolidation fracture. There's a variety, over 100 different findings you can have in an X-ray. So people are looking at specific things that they were interested in there. So one thing we like to highlight is a group we're working with in the NHS who has actually built this for neonatal abdominal X-rays. So this is not chest X-rays. Because the embeddings are so X-ray native, they're actually able to go beyond that and look at NEC, which is a condition that affects premature babies, a mortality rate of 15 to 30%. And this group had been trying to train models to identify this, really important for them, trying to train models to do this for many years and not having a lot of success. The area under the curve for their models are about 0.6. And they used CXR embeddings through CXR Foundation, and we're actually able to get a much higher AUC straight out of the box with very little data. So that's really encouraging, and they're looking to explore clinical implementation of this tool to try and help identification of this really critical finding in premature babies across the NHS. So that's what we've done as of 2022. And in 2023, we had a big push in our research team to try and align our image embeddings with language. And this resulted in this publication called Elixir, which is where we focused on trying to bring these two things together. Now, that may seem a little bit strange, but let me just explain a little bit more what the benefit of that is. So out of the box, when we do this language alignment, we found that these new embeddings actually perform better by a factor of about 2 orders of magnitude. So you need much less data for the same performance. So it sort of supercharged our classification performance in the embeddings. This is now made available in Elixir. But we also unlock some new language tasks. But once again, I might pause and hand over to Andrew to talk more about what it actually means to do this language alignment with the embeddings.
Yeah, thanks, Rory. So with the language alignment, you can basically think of taking that same embedding space that we just talked about for the images, but also bringing it closer to human natural language that gets embedded into the same space. And so then, we have to be a little bit careful about kind of how we talk about that embedding space, but to some extent, we're able to then, the regions of that embedding space become more semantically meaningful to us. So, you not only have this area or this ability to draw a circle around some finding for classification, but maybe also that is close to the words that describe that. And that's where that will unlock these other use cases that I'll demo after Rory finishes talking more about it.
Awesome. So I'll just talk about some of those use cases before Andrew explains them, but through the demo. But we think about these 5 extra use cases we have. So just to remind everyone, we got this extra performance for a classic classification task, which is, I've got an image, I want to find some condition in that, whether it be an operational, a screening, or a diagnostic use case. So it really helps us with that, but also unlocks some of these other things that I'll go through really quickly what they mean, and then Andrew can actually show you what they look like in the here and now. So the first one I'll talk about is zero-shot classification. And what this looks like is actually, rather than needing to do a classification task by providing it task-specific data, you can actually prompt the model with direct words and get out-of-the-box performance that in some cases can be really, really compelling. So for this example, we used the word effusion to predict pleural effusion in our x-rays. And what we did is we had these positive prompts where we had things like left pleural effusion, right pleural effusion. So these are examples of text that would indicate that in the x-ray there's something for pleural effusion. And then we have these negative prompts for no pleural effusion and normal. And what we're able to do is, by computing the distance between our image embeddings and our text embeddings, we're able to identify which the image embeddings was closer to. Was it closer to the positive prompts, or was it closer to the negative prompts? And if it's close to the positive prompts, we interpret that as a positive prediction, and vice versa with the negative prompts. So by doing that, you can create a binary classification without providing any data to the model whatsoever. So that's why it's called zero shot. And like I said, we can get some really encouraging performance here. In this example, we actually have a 0.9 AUC, which is really, really good, given you provided absolutely no data. In the paper, you can see what the performance is across a range of different models we put out there for different tasks, whether it be effusion, cardiomegaly. But across the board, we can see really encouraging performance, especially given that there's, like I said, no data provided. Semantic search is another use case that we've explored as well. And language and search really go hand in hand. It's what we want to be able to let users do is actually search through their set of images to find images that may match some keyword without looking at any text report that's provided. So we have this embedded search prompt where we take that and actually embed that into our X-ray space, and then compare that once again to the distances for our various images. And we can get retrieval tasks here. In this example, we've looked at endotracheal tube and actually found by sort of sorting those images by the distance, we can find images that are relevant there. So I think Andrew can show that more comprehensively in a second. What's exciting for us is this language actually allows us to do a multimodal classification as well. And so we can combine different embeddings together so that we can reflect what medicine actually looks like in practice. We're not just looking at x-rays in isolation. We're looking at x-rays in conjunction with things like lab tests, CT images, genomics, all these things together. How do we actually combine all that information together to make better predictions? Finally, we're able to actually take the image embeddings and pipe it directly into an LLM. So in the paper, we talked about an LLM called Palm, but we're actively exploring Gemini now, which is Google's latest LLM. And that allows us to do visual question answering, where you can actually interrogate the image by adding it to your prompt and then asking questions about it. In this example, we're talking about pleural effusion and whether or not it's actually present in that image. And the final one I'll talk about is taking that visual question answering concept to the logical conclusion, which is actually to generate the reports directly. And so you can ask the LLM to actually generate a report based on what it sees in that image. And we can also do the inverse, where we actually check a report that a radiologist has already written and see if there's any errors there. So we actually had that as an evaluation task in the paper, and found that if we added intentional errors, we could find that the model actually could detect them and explain what the errors were and why they were wrong, which is really, really encouraging for us. So I'll pause there. Andrew, do you want to go through the demo of some of these latest language alignment tasks that we have just released in the last week?
Yeah, absolutely. I was just finishing answering one question about pairing chest X-ray with other modalities, and it's definitely top of mind. We are just beginning to look at some of the other modalities like ultrasound. I mean, there's kind of everything is on the table in some ways. One tricky bit that we're navigating is whether or not the modalities are naturally paired with text. So lots of times with medical imaging, it may not be common to have a report with it. So, you know, are there other ways that we can pair those kind of with the other modalities and with back to the text space sort of transitively in a way? Let me go ahead and present.
Can I jump in with a quick question as well?
Yes.
I'm curious to hear about how does the performance of models vary across like geographically and demographically diverse data sets? So you're talking about a few different modalities, but what implications does it have for like global applicability of the findings?
Yeah, it's a really good question. I think there's a lot more that needs to be done to examine that. I think there's some promising early results, and we're working directly with a few groups as well who study or who have deep dived into a lot of you know, whether it's fairness concerns or bias concerns, the subgroup analysis, that kind of thing. I think it's fairly promising that it shows you know, there is bias, right? There is something built in there, but there's things potentially to work around it. And I think the important thing is to give people the tools to help track that through the model and through their endpoints. So I think it's definitely top of mind. I mean, I don't think there's any such thing as a model that's going to just magically work globally and not have considerations on that level. So the important thing is to be considering them and to actually account for them, right? Yeah, so I promised I would give a quick overview on the actual architecture, just as a quick review. I definitely refer you to the paper as a great reference for that. But broadly speaking, this step of text alignment happens first through CLIP, which is contrastive, more sort of purely contrastive training. So what you're doing there is bringing the embedding spaces of text and image together, and that's very common for natural images as well, and for these some of these massive natural image and natural language models like from OpenAI and Google. And then the second step is through a technique called blip, which is sort of another way of lining up the image space with the text space. So the way you can think of it about that is with the output of the original Chest X-ray Foundation model, or our image model, being this kind of, you know, an array of numbers, again, this kind of compressed representation. And blip is going to learn which pieces of that to feed to your large language model to then interpret. So it does some filtering and it does some kind of active matching. And, you know, broadly speaking, the image encoder is an efficient net, which is still a convolutional neural network. And we're working on figuring out how to get vision transformers to work well with it as well. They're a little harder at the larger resolutions. And then the downstream models, the large language models, are your typical transformers like Palm 2 or Gemini upcoming. So they're doing the autoregressive language modeling for that. Okay, so just to deep dive a little bit more into the use cases that Rory mentioned. So semantic search is something that is unlocked because of this alignment of the two embedding spaces. So the technical way to visualize this is that this query, this natural language, is being projected back into that embedding space that we just aligned properly. And then we're going to find all of the images that are also embedded near it in space. So in this case here, when we're searching for cardiomegaly with left pleural effusion, this is for an image that we actually don't have the report for, but we're still able to get reasonable results and retrieve something that makes sense for this query. So you can imagine this being useful for things like cohort building in a study, or similar image matching, particularly when you don't want to be searching on the exact text of a radiology report. In some cases, radiology reports may not have the full content that you would want. They might be abbreviated, or they might not mention a certain finding. So this helps with that. So in our first case with CLIP, which is already this alignment of text and image spaces, you get this similarity out of it, but there's a lack of granularity there as well. It often loses some of the context of actual localization. So it could do things like here, it does central venous catheter quite well, gets pretty high similarity on that instrument, or that support device. But then it will fail on some other things, which I'll show you in a minute. So the second stage of BLIP2 actually does this image text matching. So first stage, we just get this raw kind of similarity between the whole query and the image, and we get this large candidate pool. The second stage actually does a binary classification of does this match or not. And this helps us re-rank that larger candidate pool. And so for evaluation, we kind of try to put it to the test. A lot of times I think the text to image retrieval tasks out there might be a little too simplified for the medical use case. For example, if you wanted to search by laterality or severity, if you search for left pneumothorax, we kind of want to consider it to be incorrect if it returns a right pneumothorax. It's maybe partially correct, which here we're giving kind of a 1 out of 2. So it's relevant, but it's not perfectly precise. And only if it matches everything in the text does it get a 2. And this is going to be graded by radiologists in order to have the ground truth there. So in the very bottom case here, also the nuanced features, you can see that we're searching for kind of combinations of findings where we really wanted to match all of them, or a very highly localized, or combination of localization plus severity. Those are all kind of our more difficult use cases. And you can see BLIP, Elixir with BLIP performs the best. It does well on both precision at considering the top 5 results, as well as our specialized text-to-image retrieval metric, normalized discounted cumulative gain, I think it stands for. And qualitatively, we can visualize this with kind of some of the error cases for CLIP that are done well with BLIP. So you can see when we search for small right pleural effusion and no left pleural effusion, again, the CLIP on the top, on the far right, you can see we often will return something that has a small left pleural effusion, but no right. So it's kind of getting it correct, but not exactly. Whereas on the bottom, we get full matches. So we restore some of this more specific language about locality. I wasn't paying attention if we had any questions. I can pause there for a second, or if Rory's handling them, that works too.
No questions. Keep going.
Okay, awesome. So looking now at visual question answering VQA with Blip2 and Palm2. So this is the next stage of training. The whole training process for Elixir is what we call curriculum learning, where we started with this image text contrastive learning with Clip. We trained this first phase of Blip, which is a relatively small language model, and then now we're at the final stage of Blip training phase 2 is to link it to a large language model. There's some advantages of this, which are that you can actually leave the large language model frozen, the image model frozen, and you're training just this adapter between the two. We call it model grafting. It's one of a number of techniques that are out there already, and this allows you to kind of plug and play a little bit. So you should be able to train to a new large language model relatively easily, without massive amounts of compute. And of course, we're obviously also investigating some of the other end-to-end fine-tuning cases. But it's with this large language model that you get the capability, the more natural language capability of, say, visual question answering, or what we'll talk about in a second, the report quality assurance. This has the more conversational, like the instruction following ability. Oh boy, I don't know if this is going to work. Oh, is that working?
Yep, working well.
Okay, awesome. Hopefully it just keeps playing. But the idea here is that again, it's similar way of a not exactly zero shot, right? I mean, we are clearly providing it some of this information, but for the most part, we've only trained this on radiology reports. But then we're able to actually frame things in the form of questions, and oftentimes it's questions that aren't directly addressed by the original radiology report. So I mean, things like what organ is in the image, or what type of image is it? Obviously, it's gathering that from the context. Then we're going to push the limits and ask things like, what treatment would you recommend? What drug compound? And obviously, it's going to, in some cases, not get it perfectly right, but it's leaning toward that. So we're kind of giving it more and more of this context. And you can imagine that there's some use cases just in educationally. If you are training to become a radiologist, maybe this is a great way of bootstrapping. Maybe it's just you want to look up your own image and you are not a radiologist and you want to ask questions of it yourself and understand the report a little bit better. That's another possible use case. Or maybe it's a very complex case. So we're definitely well aware that some of these things, we don't want to be slowing down radiologists. We want to empower them and other clinicians. So maybe we're up-leveling non-specialists, or we're empowering those who already have the expertise to kind of have more expertise or have more retrieval ability. So that's another use case we're very excited about. You can see, again, we've kind of put it to the test, and we'll have some results coming out shortly that better contextualize this as well, comparing to other large language models that are out there, or large vision language models that work in this space. And the accuracy on both the kind of the simpler yes/no questions that pertain to things like your presence, the location of a certain finding, it does better. And then we push it even more with things like the size, severity, and the type. So the much more difficult questions. And this now gives us a benchmark that we'll be able to hopefully release as well, a data set that other people can try and improve on. So things that's a little bit more rigorous than VQA RAD, because we know that in VQA RAD, there's actually this test set leakage, and it's fairly easy to sort of train to do well on the test, but not do great on the out of distribution questions. So finally, before we do our quick demo.
the QA bit, just got a question on like localization of the model and like its ability to understand where classification is coming from. So are you able to talk a little bit about that?
Oh yeah, so the model has no capability of it does, and it does to some extent. I mean, you're absolutely right that there are more and more techniques almost every day that better enable this. The kinds of cross attention to the actual outputs of the vision model, or building that into the vision model so that it's much more fine-grained, is, you know, and a specific detection or segmentation head might actually help that as well. So that then it's able to kind of point on a, you know, multiple, or, you know, sort of patch level basically, or, you know, a few pixels really to actually localize it. So I think this is just scratching the surface of that for sure. There's always this balance of where do we have data and where do we don't. So having detection and segmentation labels certainly helps, but we don't always have that for everything. So we have to try to balance between when we have those labels and when we don't, and how do we get the model to kind of learn in both cases. So hopefully that answers that question. So last, before we do a quick demo of Superbio's capabilities with Chest X-ray Foundation, I'll talk about the last use case here, which is report quality assurance. So again, kind of pushing the boundaries of what we think things are capable of right now, but also considering what would be useful in a clinical context. You know, again, we have this sense that we don't want to be slowing down radiologists, but there's a lot of understaffing right now, and there is a very real need for catching errors, right? Whether it's from being overworked, or just the simple sort of, you can think of them as typos that we would make when we're typing up a document. It could be the same thing for writing a radiology report, in which maybe you invert the laterality, you say left when you meant right, or you forgot to add in something about a certain finding. And this would be a more sophisticated kind of spell checker for your radiologists. So the hope would be that it's kind of running in the background, and when you go to submit your report, maybe it says, oh, I think you meant left when you said right here. And that would help catch these things before they propagate. So this was a slightly more complicated prompting process, although I think we're making progress on making it simpler. But essentially what we did was to ask Elixir to generate a report based on a series of questions that we asked it. And then we fed that report to compare to a candidate report and say, you know, do these look the same? And if not, what is missing? And that helps the model hone in on what might be wrong with the candidate report. So you can ask it things like, you know, or why is this report wrong? And it's because, oh, this finding has not actually resolved, even though you said it did, or you missed, or, you know, this pneumothorax is actually on the left and not the right, that kind of thing. So again, some pretty encouraging results. A small caseload right now, but working on bumping that up as well. And again, hopefully we might have some ability to release a data set like this, or better improve the benchmarks that are out there. And again, I think tuning for a case where we have the high confidence in certain detections might be a great starting point here as well. But always targeting this use case of kind of augmenting the radiologists and really empowering them to better do their jobs. So in terms of next steps, as Rory mentioned, I think we see chest X-ray really as a starting point for a number of good reasons. It's a very ubiquitous modality, but as someone in the comments pointed out, and there are definitely locations where it's not as ubiquitous, and there are other modalities that are more. So we want to expand to them. So that's both within radiology and outside of radiology, and outside of and in the broader space of medical imaging, but also even beyond in sort of genomics, other things that inform your the health of a person. So we're looking at general X-ray, mammography, lung CT, as well as pathology, dermatology, and can we kind of put this more multimodal, fuller picture of a patient together, which is exactly how medicine already is, right? There's this kind of multimodal synthesis that's going on. And then clearly, as you know, being here and working with Superbio and so on, we're very keen on these kinds of collaborations that are building tools on top of CXR Foundation, but we're trying to get to the place where care or research or anything is being done, and we may not have everything that is needed in order to do that at Google. So how do we get it into the hands of the folks who do? That could be data, that could be expertise, that could be access. So all of those things are sort of last mile problems that we think they're definitely the most important, and they might also speak to why there hasn't been as great of an adoption of AI in medicine as there could be. And another great tool for this, of course, is cloud. And you know, if cloud, if you don't want to have any of the or consider all those problems of kind of serving your model and scalability and everything, maybe you kind of offload that to cloud and then build on top of that as just a component of something much larger. So I'll pause there. I guess we can take questions now, or Rory can do a quick demo.
Yeah, just to build on that last point, Andrew, I think we kind of have two ways you can consume the Elixir model at the moment. We have coding notebooks, collabs that you can use, and that they're a little bit in the weeds for users. Like you have to sort of play around with code. And obviously, we're really excited to work with Superbio, who has more of a click, very simple user interface that we'll demonstrate in a second here. So if you just have data and labels, you can really get started training something and deploying that offline. So it's nice to have that full spectrum of accessibility depending on what's important to you. If you really want to tweak all the knobs and the little levers in terms of training, maybe the Colab is the right approach. But if you really want something that's quick and easy, Superbio is a great platform for that. I think we had a question about use cases for the autocorrect feature. We have a lot of physicians on staff, and we've talked to a lot of people about their QA interest in it. Of course, it's something that we're still exploring how to actually make that operational. The demonstration is more sort of researchy, but I think as the performance increases, then that becomes something that is feasible to deploy. So we're at the very beginning of the journey, but there's a lot of excitement about radiologists not needing to look at AI directly, but just getting a notification after the fact rather than influencing and interacting with their workflow directly, which can sometimes distract them. I think Daniel was talking about ophthalmology, and something that we've thought about a lot. We have a group in the UK who actually built a model called RedFound, which is a foundational model for ophthalmology. So some people are exploring that, and we're really excited by the direction of that work as well. I think we've answered the question on cost. So maybe I'll just jump to the Superbio demo, if that's okay. So this is Superbio here, as Burke introduced before.
Rory, maybe it's just me, but we can't hear you again. Nope.
How about now?
Yep. Can hear now.
Yeah. Zoom wants to keep changing my microphone for some reason, which is really fun. Anyway, as I was saying before, we just demonstrating the Superbio platform. So I've searched for CXR here. We have terms of service that we require people to sign up for. So you get a notification there that just gives that information. the important thing about the terms of service is this is a research tool. So at the moment, we're not giving people the permissions to actually train things to deploy in the real world right now. This is just to experiment and kick the tires on what it can do, and then hopefully we'll be able to expand usage of that in the future. So once you've got access granted, you can use Superbio to upload both labels and images. So Superbio actually has some demo data that I'm just going to use in this case. So they have some TB labels. So select those. And then what I can do is basically kick off the amount of epochs I want to train for and the amount of trials I want to train for. So I'll just crank them down all the way down. I sign up to this and then submit job. And I run this on GPU. And I've got that here. So here's one I prepared earlier for this demo. This is for tuberculosis, so classification of tuberculosis. The training loss goes to 0 because the data set's very small. So you have to sort of, you take that with a grain of salt. Obviously, it's not a perfect model, which is what's showing here. But you can then deploy this model, I believe, and then take a test set and actually evaluate the test set to see what that performance is on an external data set. So really simple to get started. My other job is, I think, running now. And that'll take a few minutes, but once it's gone, I'll get that same model that I can deploy. And Berk, you're the expert on this platform. Anything that I've missed here in this demonstration?
No, this is great. Thank you, Rory. So if you, as on the right, you can also download predictions, then you can click on Save Model to My Model, the second one. So if you name this model and give it a little description, you can, you already created it. Okay, so using our platform, you can actually click on the right, the 3 things. You can actually go for inference and training a new model with the stage model. If you go above a tier, which is a boost tier, which we just rolled out recently, so it's like a premium feature that we rolled out. But this is all there is. Thank you so much for going through this, Rory. I think there are a few questions about the app on the, especially from Ranjan Nag, what's the difference between trials and epochs? If you could talk a bit about that.
Yeah, I was actually asking, is that for cross validation versus epochs, or versus per trial epochs? Is that correct? Or
yes, that should be correct. Yeah.
Yeah. So the number of trials is the number of different models you might train, and the nice thing, one other nice thing here is that because the models are so quick to train, you can try it multiple times and kind of see the effect of different hyperparameters or initializations. And then epochs, given if it's a small data set, you probably don't need that many per trial, but you could go through 10, 50, 100 epochs. Yeah, exactly. A trial can, each trial can go through all of those epochs. They can pass through the data 10, 50, 100 times. And then the different numbers of trials might give you different models as outputs. Yeah, but we definitely wanted to say how we're always on the lookout for how to improve this. We know that the collabs and things that we put out are just a start, and tools like Superbio are a great way of getting better acquainted with this in a less kind of down to the code level, and improving the usability and the kind of lowering the barrier to entry is always top of mind for us. So we definitely want people to reach out, give feedback, tell us your use cases. A lot of it is things that we didn't consider beforehand, or better ways to kind of mold how we're thinking about future use cases. But yeah, I'll definitely pause there for any other questions that people have.
Everyone has my email, so feel free to reach out to me as well. If you have any questions, I can pass it to Andrew and Rory. I think this is it for now. Well, thank you so much, everybody, for joining. I guess there's the last question. What's the format of the data? I think it's also available on the the platform itself. If you want to talk about it a bit.
Yeah, I can talk about the format of the data for CXR Foundation, and then there may be some nuances to how Superbio is actually formatting it to pass beforehand. But roughly speaking, you need a set of images, which for Superbio could be a zip file, or with the collabs that we have online, it can be a bucket, a Google Cloud bucket. And then a file of labels. So it will say 1 for your class, 0 for negative of that class, and then it can train a model based on that. Some of the newer use cases that we just mentioned today, like semantic search, there's demo code for that available as well. So you can retrieve images based on a given query, and then we're going to be adding things like the zero shot as well. So yeah.
Awesome. The latest updates that Andrew and Rory went over will be available on Superbio in no time. It's just recently released, so our team is working to update the existing app as well. But please sign up, give it a go. You can, as you've seen, there's a demo data to just run and try it out. So you don't have to bring in your own data if you don't have any right now. And please let us know what you think. I'm also sharing, we also run a large language model course called LLMs in Healthcare. If anyone's interested in taking a look or joining us, sharing a link below. I will share the recording with all of you. Thank you so much for joining, and Andrew and Rory, thank you so much for going over the wonderful research that you've been doing and demoing Superbio. It's been great to have you.
Our pleasure. Thanks so much for inviting us.
Yeah, thank you so much for having us, and thanks to everyone for joining.
All right. Thank you. Have a good one, everyone.